let me know when you guys can see my screen, and let me make the fonts as big as possible.
Yeah, I can see.
So you all know the answers, but I'll go over it. What are the typical uses of a decision tree? A decision tree we use for both regression and classification. That's why we call it, people often call it CART, classification and regression, the algorithm. Right? It can not only be used for classification and regression, it can be used for a dimensionality reduction and for clustering, though uses in those contexts are not so widespread. And generally, people tend to use other algorithms for clustering and dimensionality reduction. But for classification is very, very popular. It is also used for regression. So that's that. The second question is, what does Ginny in the decision tree algorithm refer to? So, by the way, how many of you went for C in honor of an old school chum named Ginny?
That was just entertaining.
Right, okay. And so it's a thing that actually I myself learned while teaching this workshop in a previous time. I wondered what Ginny, and then I learned about this great mathematician, a statistician and sociologist, Italian, in 1800s. So it is his work. It's an impurity index. Now, what is information gain? I'm very proud actually to say that the information gain question now all of you got right, because in the previous survey, it was the question whose understanding, like when I said, how well do you understand that? It had gotten the lowest score. So I'm very happy to see that we finally got information gain. Nice. Even this loss function, very pleasantly surprised that most of you got it right. So in the loss function, the terms are, this term is the sum squared loss. You see the residual squared and summed. And then alpha is the regularization parameter, and t is the number of nodes in the tree. What you're basically saying is that the more the nodes in the tree, the bigger the penalty. Right? Oh, by the way, is it plus or minus? I forgot. Okay, I might have made a mistake. It might have been a plus, depending upon how you interpret alpha. But basic point is that if you increase t too much, you will actually it should have been plus most likely. Okay, if the number of nodes in your tree is high, you penalize for that. This is just a sum squared error. No, it is not enough, because then it will overfit. This is the part that introduces pruning in the tree. Then this is a question that keeps coming up. People say, decision tree, is it inherently more powerful? And in general, will this outperform a linear or polynomial regression? The answer to that is actually no. There is something I keep talking about, the no free lunch theorem. No free lunch theorem is one of the, I don't know how much I talked in this particular season, but it is one of the great landmarks, not just of machine learning, but in the theory of human knowledge itself. Like, it is in the same class as Gödel's incompleteness theorem. It's very, very powerful. It came about towards the end of the century. And what it basically says is that all these theorems say is that no one algorithm is more powerful than another. Any two algorithms, if you compare, there are situations where one will do better. There are situations where the other will do better. In the case of a decision tree, you notice that it divides the feature space into regions. So any decision boundary it makes will be sort of staircase-like, step-like. Okay. And so if the underlying ground truth is a linear decision boundary, it will do extremely poorly. Well, I wouldn't say extremely poorly, but it will approximate it. I take that back. It will approximate it, and in the asymptotic limit where you have a very deep tree, it may get it right, but a simple straight line linear regression will outperform it. The same is true when you do polynomial regression. Polynomial regressions represent, well, some sort of a surface or shape in the feature space, a smooth differentiable shape. Decision trees make edgy, they have sharp edges. You know, their decision boundaries are anything but smooth and differentiable. It's the opposite. So that is that, both for, and this thing is true for classification as well as regression. If the underlying ground truth is a straight hyperplane, that relationship is hard for the decision tree to capture. Though in the asymptotic limit of a really deep decision tree, it can. It can make very small steps and get it right.
So Asif, what is the asymptotic limit?
Oh, asymptote means in the limit of very large numbers. So for
So that's
example,
like minus infinity to plus infinity, or?
in the depth of the tree, no? The
Oh,
size
okay.
of the tree goes to, yeah, I should clarify that. When the size of the tree goes to infinity, very, very big tree, you realize that then those steps will become very tiny steps. They will begin to approximate a straight line. Do you want me to illustrate that? I could do that by making a drawing of it.
Yes.
Yeah, let me do that. I'll
So
share
I
this screen.
I have some doubt about this question. So basically, yeah, I mean, you can go ahead. I can put my question later.
Give me 1 second. Let me answer this one question, and then we'll come to your question. So what we are saying is, imagine a feature space like this, a feature space. And imagine that your decision boundary should be a line, right? Or maybe I'll just take a different color to be more exact. Sorry, Control Shift Alt H. Good, that was it. So suppose you have a decision boundary that should really be this. This is the underlying ground truth. You realize that a logistic regression will quickly discover it. But in the case of a tree, what will happen is, but for a tree, see what will happen. It will start create, because it makes rectangular decision boundaries, it will go like this. Right. So remember, it can only split along the axis. Anil, you see what I'm talking about?
Yes.
Yes. So what happens is, if you increase the number of regions, the splits, then there'll be more and more, tinier and tinier steps, and they will gradually approximate the red line, right? So the steps here, the steps in the limit of approximates the line, the true decision boundary. That's what I'm saying. Aditya, you had a question?
Yes, so I was thinking that in decision tree, like in general, it will be more powerful, means you will get a better accuracy factor. But of course, in a particular case, like we saw in case of the river data set, right, that your basically polynomial regression and doing all this feature extraction gave us the best accuracy.
Right. In fact, if you remember what happened in the decision tree, in the river data set, it was the worst algorithm.
Right, right.
It was the worst performing one. And so that is a very deep truth that unfortunately most people doing data science don't know. The no free lunch theorem. It's a very powerful result in this space. I would say it's one of the things I emphasize a lot and should be emphasized a lot. No one algorithm is more powerful than another. Get out of the mentality. The people write research papers. Researchers will say, look, how much more powerful is my algorithm compared to the other existing algorithms. It shows a level of ignorance. Contextually, it can be. So for example, for a particular task, let's say ImageNet, image classification, some algorithms certainly outperform. For a specific context, you can have a hierarchy of, I mean, you can have a ordering of performance. You can have the best performing, the next best, and so forth. So for example, for ImageNet, a lot of innovations have come because every year somebody comes up with something better. But now ImageNet has become useless because accuracy is almost near perfection. But for example, when Microsoft came out with the residuals neural network, it was a breakthrough, right? But then when VGG came out, that was a breakthrough. Then when, you know, all of these ideas, as they keep coming out, they are breakthroughs. So yes, for specific situations, one algorithm can be more powerful than another. But in the general, you cannot say that this algorithm is more powerful than the other without the context of data.
Asif?
Yeah.
What about the CART algorithm?
CART is decision tree, classification and regression tree.
Isn't it better than just simple regression and logistic?
That's what I'm trying to tell you. Remember the lab we did on decision tree on River? What did it show? A decision tree underperformed feature engineering, and it underperformed the random forest for that data set, and for the flag data set, and for the, I think also for the California housing. California housing, I think it came close. They were the same values.
But why doesn't it just like not divide it into regions and just reduce it into like a simple regression?
See, the thing is, this is what I'm trying to say, that because it splits along the axes, along the feature axes, it can never beat a diagonal decision boundary, if the diagonal decision boundary is the truth. Or any slanted decision boundary, because you'll have to approximate it here. Do you see that? You'll have to approximate it here using steps. You see that, right?
Yeah.
That's the main problem, because underneath it, there you can imagine that there are these regions, right? Regions in which, suppose it was a classification problem, you're saying this is plus, 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 and the other side of it, you're saying minus, minus, minus. So that's how you you have to deal with rectangles, and the rectangles have to be aligned by the axis. So you don't have a choice. That's a problem.
Okay.
All right, guys. So should we continue?
So Asif, means similarly like related thing. So like for the random forest, we said that. So like the split, like no. So for the decision tree, like we made the split along the axis. So there was a case of like in our data science, like the Saturday dataset class, we studied about isolated random forest, where instead of making the split along the axis, like we made it along an angle.
Yes, yes. So that
So
is
that like similar intuition or?
yes. So the idea is that you can actually split along different directions, and you have adaptations of a decision tree, but that makes it another algorithm, which we didn't cover.
Okay.
And that algorithm may be more suitable, right? So the point is that, you know, no one algorithm, so suppose you take that algorithm, I can easily show situations where it would not work. Even with slanted decision boundaries, you realize that any smooth curve is never representable with this, because it will always make these edgy decision boundaries, step-like decision boundaries, isn't it? It's the nature of it. It will not do very well. Suppose I give you a curve like this. Now what do? Or a hypersurface like this as your decision boundary. You realize that now you are stuck.
Yeah.
You can never do that, because the decision boundaries are inherently non-differentiable at these points, you know, at these edge points. You need a classifier that builds essentially differentiable decision boundaries, smooth decision boundaries in simple terms. And this class of algorithm doesn't do that.
Asif,
Yes, go ahead, Madhav.
yeah, so is it fair to say, right, if we see a data set, but somewhere locally slanted, other where it's straight decision boundary. Here you can apply logistics, other you can apply decision tree
Yeah,
kind of thing.
that is called piecewise. What you do is you do that quite often. You apply one set of algorithm in one region of the feature space, another set of algorithm in another region of the feature space. So I'm giving you a big hint. Look at the California housing data set.
Yes.
Remember last time I talked about outliers. We did not do outlier treatment. But since you took that boot camp, if you recapitulate what we did in the boot camp, right, was that we did outlier treatment. And quite often, you not only detect the outlier, you say that for outliers, I'll build a different model,
Yes.
right? Or for certain, or you can do piecewise division, or even of the inlier points. If you notice that the behavior is materially different in different regions of the feature space, you make different local models. Right? That maybe is a good segue into a topic. Suppose you have decision, let's say that, suppose you have this as a curve. What you could do is you could divide this into regions, piecewise regions. And for each region, you can make a straight line. Do you notice that? Suppose I do this, right? This. And so you piecewise, you put these things together, right? Small regions of the feature space. It is a technique. I didn't teach it because, see, machine learning is filled with so many algorithms. Do people use it? Very much so. Right? In fact, the approach of Loess and using a kernel, when we do kernel machines, remind me that I cover this, because our next topic is after boosting is kernel machines.
In this case of output, in case of classifier, the output is majority of, or output is an average of classification?
No, majority. You can't take an average.
Okay, that's what I was wondering. Majority, good.
So guys, can I now go back to the quiz? Any other questions?
Yeah, so I just one comment. So in the previous case where you had drawn that linear one with the rectangular like steps, so in the limit that this width of the rectangle goes to 0, then it will approximate to the straight line, right?
But you realize that you have severely overfit to the training data.
Right. Yeah, that's true.
That is the main problem. And hold that thought in your mind, because we are coming to that question.
Okay.
So the next question is literally that. The question was, one of the inherent advantages of the decision tree is its robustness against overfitting to the data. Right? In fact, it is one of the demerits of a decision tree. When decision tree came out, it overfit. People realized that it could fit to nonlinear data, like it could fit to nonlinear surfaces or decision boundaries and lines for regression, surfaces for regression, but it overfit. So they said, no problem, we'll prune the tree. And there was a huge set of activity creating smarter and smarter pruning and faster pruning implementations. The trouble with pruning is, even if you prune, you tend not to get rid of the variance errors. It still remains residually overfitting. If you try to overprune, then the bias error shoots up, right? So you're left at a hard place. Your minima between, the optimal point between the bias variance trade-off still leaves you with a lot of errors. And most of those errors come from your variance part, the overfitting part. Right? Which is why, if you go back to our random forest, which we covered this week, what is the advantage of random forest? You take a lot of trees. And because you take a lot of trees, it has, it blurs the optic. It is almost like you're looking at the picture through a camera in which you deliberately defocus a little bit, right? So you smooth out the very small steps or things like that. So you end up decreasing overfitting. You never get rid of it, actually. The inherent problem with this trees and tree-based algorithms, even ensemble of trees, is it is very hard to get rid of overfitting. So there's random forest. Better than that is extremely randomized trees, and so forth. There's a whole set of improvements. It was a cottage industry, like lots of people created lots of variants of the decision tree ensembles. And they all, to different degrees, address the problem of overfitting. They work. I mean, in very popular for tabular data, if you go and look at Kaggle, you notice that most of the winners of tabular data are random forests and boosting algorithms, XGBoost, CatBoost, this, that. They are all tree-based algorithms. So trees are here to stay, but you need to not just use the decision tree, you need to use ensembles of them. All right?
How will you know all this once if you start doing black box model like deep learning? You will never realize all this.
Yes. All right, guys. So now I'll share back to the quiz. Oh, am I already sharing the quiz? No. Okay.
Yes.
No, you are.
Yes. So here we go. So the next question, guys, is decision tree is inherently more, as it will outperform logistic.
Can't hear the audio.
Yeah,
Because a decision boundary that is not. Oh,
so we lost you in between.
sure. Can you hear me now?
Yeah.
Okay.
Yes.
The thing is, this question that decision tree is inherently more powerful, that in general it will outperform logistic regression. I hope I don't need to explain anymore. We saw that it's not true. If your decision boundary is a hyperplane at a slant, decision tree will never outperform a simple logistic regression. And it again goes back to our no free lunch theorem.
Mm-hmm.
And now to the last question, guys, which is
Entropy.
the probability of is P. Then what's the definition of entropy? So entropy is defined as minus P log P. The minus sign is to just, because the log of a number, probabilities are between 0 and 1. So the log of that will always be negative. So to make the negative into positive, you use this minus sign, a P log P. Right? Now, log to the base what? Depends upon which community you're talking to. If you're talking to the decision tree or this sort of community, they'll say, okay, log 2. Or if you talk to the physics community, they'll say log, natural log, right? Information theoretic will say log 2 and so forth. So those things we can sort of minor aspect, but that's about it. So guys, that was the quiz for today. I hope you found it useful.